Hello, my name is Albert Thompson. Today I'll be talking about helicopter components, specifically from the R-22. Some of the materials I'll be using today are from the Aircraft Line Handbook, and my R-22 POH. So the R-22 is a single rotor, single engine helicopter, two-seater, with removable doors. It's primarily made of steel tubing and riveted aluminum. The tail cone is monocoque structure, so it's kind of like a soda can. It gets its strength from there. So if there's any dents in it, the strength of it is compromised. So make sure to check that during pre-flights. And also there's a skid type landing gear system, which seems to be the most common type. You can also have float type skids for marine operations, or for our wheel type land gear, which seems to be reserved for larger helicopters, but not limited to, such as CH-47s, or Chinooks, or UH-60s, Black Hawk, Sikorskis, something like that. So an R-22 power plant is a Lycoming 4-cylinder horizontally opposed piston/reciprocating engine, and that operates on a 4-stage system, which I don't know if you can see right here. Intake, compression, power, and exhaust stages. I don't have a picture for that, but I'll try to explain as best I can. A piston is going up and down this shaft. When it's open, there is an intake of your fuel-air mixture. The piston closes, which compresses the fuel-air mixture. It's then ignited by a spark plug, which will cause the fuel-air mixture to burn and provide our power. Then the exhaust gases are then pushed out of the cylinder, and that's pretty simple. The spark for the burn is provided by our magnetos, which run separately from the aircraft's electrical system. So it'll constantly provide that spark that we need to keep power running and efficiently too. So the engine is also depending on what type of aircraft. We're flying Beta 2s running on 145 brake horsepower, D-rated. What that will do is extend the life of the engine to 2,200 to the overall hours. It does that by reducing the amount of power it's increasing the power available for just day-to-day operations. So that's how we do that. So this is a very crude drawing of our engine and our drive systems. So we have our engine here, and we need to get power to the main rotor and tail rotor. So we do that with a drive system. Our lower sheave and upper sheave are connected with V-hubs. Now, when we crank the engine, to have all this connected together would provide a very rough start for the engine, to have all the weight of the rotor system on. So these belts need to be loose. So we can crank the engine and then tighten the belts up later, so we eventually get the power to the main rotor system. We do that with a clutch, belt-driven clutch to be exact. So crank the engine first, and then we activate the clutch, which is part of our post-crank checklist. And then we'll tighten these bolts and eventually get these drive shafts to start turning, and then the main transmission, and then these rotors. So just to take the stress off the engine. Now, in the reverse of that, in case we have an engine failure, we need to have a way to disengage the engine from the rotor system in order to maintain our RPM. And we do that by using a freewheeling unit. what will happen is that that free rolling unit will automatically disengage the rotors from the engine once the engine RPM is lower than the rotor RPM. So the engine is no longer a factor, so we can control our rotor RPMs from there. So let's see. So now that we have our engines cranked, our belts are tightened, and now that the drive system's going, turning our rotors, our transmission's job is to transfer engine power into rotor RPM. And what that does is it reduces or increases the RPM provided by the engine into the optimum amount of RPM to keep you in the air. So let's see. So the main rotor systems of the R22, we have a semi-rigid main rotor, which means that they can flap and feather. Flap, which moves the blades up and down to compensate for symmetry lift, and feather to change the pitch angle of the blades. Now, compared to the other two types, the rigid, which only does feathering, and the rest of the rigid system provides you see, it absorbs forces through blade bending. So there's that, and then the one stage up from there was fully articulated, which can flap, feather, and hunt, which means the rotor blade can move forward and aft. That's for Coriolis force, so hopefully we can explain that later. So that our main rotor system will be able to provide our lift and thrust for hovering and forward flight. The R22's main rotor blades, like I said before, there are two. They're symmetrical in design. They're a little more stable than asymmetrical. Now, our tail rotor is designed to be an anti-torque system. So, what that means is that, according to Newton's law, third law, for every action there's an equal and opposite reaction. So the blades are turning counterclockwise. You can see that. So that means the fuselage of the aircraft is going the opposite direction. So to counter that, the tail rotor provides thrust in the opposite direction to make it nice and level during hovering flight, or just nice and level. So what that means is that the power is needed to have the engine provide thrust in the opposite direction. So that means in order to provide left correction or left pedal, you're going to need power from the engine. And the opposite of that is if you need right pedal, that means you're reducing the amount of engine power that you need. So, I think that this was that does it for helicopter components.